Hello my dear students, in the last class I explained to how to find I moment of inertia for the T section and calculated Euler's crippling load. Today's class we will discuss how to find moment of inertia for I section and calculate the Euler's crippling load. Let us take this example. An I section joist 200 mm by 400 mm by 20 mm and 6 meter long is used as a strut with both ends fixed. What is Euler's crippling load for the column? Take Young's modulus for the joist as 200 GPa. What is given here? The outer depth is given. Okay, this is the given I section. Okay, here this is 200 depth and breadth, overall breadth 200 and depth is 400. This is 400 and thickness is 20 mm. This thickness is 20 and here also this thickness is 20 mm and overall length is given, that is 6 meter, the length of the strut. So you can convert into millimeters, 6 into 10 raised to 3 mm. Then the modulus of elasticity 200 GPa or 200 into 10 raised to 3 Newton per millimeter square. Okay, first you have to calculate I here also, because Euler's crippling load is PE is equal to pi square EI divided by LE square. So here all data are given except I. So you have to calculate I. What you can write here, from the geometry of the figure we can find that inner depth, okay, this is capital depth. Capital B is 200 and capital D is 400. But small d, that is 400 minus 20 minus 20. That's why 400 minus 2 into 20. That is inner depth, okay, is equal to 360 mm. Then inner width, the total width is 200. You have to deduct this, that is 200 minus 20, that is 180, that is inner width. Okay, what this I section, what is the formula for I section to calculate I is 1 divided by 12 into capital BD cube minus small bd cube, or BD cube divided by 12 minus small bd cube divided by 12. You can write individually or you can take 1 divided by 12 outside and capital BD cube minus small bd cube. Here, why this is deducted from the overall? See, first it was considered this as the full rectangular section, that is capital BD cube divided by 12. Okay, that is capital B and capital D. You have to deduct this portion because we want only this portion, I section. We want this I section. So first it was considered as rectangular section. From the rectangular section, this portion was deducted. Okay, that's why this is the formula, 1 divided by 12 into capital BD cube minus small bd cube. Small bd cube portion we are deducting because we want only this position point, this portion. Okay, now we know what is substitute the values in this equation. What is capital B? Capital B is 200 and capital D is 400. Okay, so 400 BD cube, so 400 cube into 200 minus small b. Small b I have written here 200 minus 20 means total B is 200. We have to deduct this point. We want only this, that is 180. 200 minus 20, 180 into D. This depth, that is what? 400 minus 40, that is 360 cube. Okay, so simplify this, you get 366.8 into 10 raised to 6 mm4. This is Ixx. Now you have to calculate Iyy. That is same method what I have taught in T section, that is B cube D divided by 12. Here there are 3 sections are there. So that 3 times you have to write B1 cube D1 divided by 12 plus BT cube D2 divided by 12 plus B3 3 cube d3 divided by 12. Or these first two sections are same here. See here, this and this are same. So you can write 2 times of 200 into 20. That also you can write, okay, in order to simplify the calculation. So I have written that, although the equation is like this. So 2 times of 2 into that is sorry, this is not 2, this is 20. 20 into, okay, this is 20. B is sorry, not B, depth. Okay, here this is B cube 200, and no, in this is, yeah, and D is 20, but here we want B cube is B cube into D divided by 12. So that is why 200 cube into D divided by 12. It is both top and bottom, it is same, that's why multiplied by 2, plus here in this case that is D is 360 into B cube, that is 20 cube divided by 12. Okay, so simplify this, you get 26.9 into 10 raised to 6. So which value you have to consider? Lesser value you have to consider. What is the first value? That is 366, and here you are getting that is 26.9. So IYY is less than IXX, therefore the joist will tend to buckle in YY direction. Thus we shall take the value of I as IYY, that is 26.9 into 10 raised to 6 mm4. And now the column is fixed at its both ends. Therefore equivalent length of the column is equal to LE is equal to L by 2. So this is based on the 4 end conditions I have given in the, I have mentioned in the last class. For the different end conditions, the L effective is different. So you have to consider which is suitable to your particular problem. Here both the ends are fixed. That's 4 LE is equal to L divided by 2. L is 6 into 10 raised to 3 divided by 2, that is 3 into 10 raised to 3 mm. Now you can use the formula Euler's crippling load, that is PE is equal to pi square EI divided by LE square. Pi square into E is 200 into 10 raised to 3 into I is now 26.9 into 10 raised to 6 divided by 3 into 10 raised to 3, that is LE square. Okay, you get 5.89 into 10 raised to 3 Newton. Okay, so like this you can calculate what is the moment of inertia and what is the crippling load. Okay, here this is very simple problem. I mean, if the I section is symmetrical, you can use this formula. Okay, if the I section is of unsymmetrical, means both the flange and both the flanges are of different sizes, then you cannot use this formula. Okay, this formula is applicable only for the symmetrical I section. Suppose now flange here it is 250 into 20 and here 200 into 20. You cannot use this formula. You have to find IXS using the formula what I have taught in the T section, that is IXX is equal to BD cube divided by 12 plus AY square. That formula you have to use. This formula is applicable only the I section is of symmetrical. Okay, otherwise you have to use the different formula, means you have to locate the position of the neutral axis. Here the neutral axis lies exactly at the center, okay, because of symmetrical, but in the unsymmetrical section neutral axis is not at the center. So you have to locate the position of the neutral axis, then you have to calculate the moment of inertia. I hope all of you understood. We'll take some more examples in the next class. Thank you.